Alright everyone, so in the last lesson before you were all home, we were starting our discussion about projectile motion. So just to recap, projectile motion is basically two independent motions happening together. You're going to have a motion which is up and down. So you're going to have, for example, someone is throwing a stone, or I don't know, a soccer player's kicking a ball, right? So it's going to be thrown forwards but also upwards a bit. So since there's gravity acting on it, its motion will be like a parabola. So my drawing skills with this are terrible now, but it's going to be something like that, right? Depending on how much air resistance you're going to have, you will have different shapes. So if there's no air resistance, this is going to be roughly the shape that it gets. If there is air resistance, it will decline quicker, alright? The point is, this top will happen before, and also it's going to fall earlier, so sooner, so closer to the point where it was thrown. So and there are two independent motions. So the horizontal motion is constant, so it doesn't change if there's no air resistance, right? It doesn't change, so it will remain its movement forwards, and it will keep constant, the movement forward. It will only stop because it's going to hit the ground. The movement upwards, however, it will change. I mean, the velocity will change. It begins as a velocity upwards, and then as gravity acts on it, it will slowly decelerate. So it's going to slowly decrease its velocity up to 0 when it reaches the top, and then it's going to accelerate downwards. So its velocity is going to reach 0 here. The vertical velocity will reach 0, and then it will increase as the object falls down. So let's take a look at one example. So a student drops a stone from rest at the top of a well. So we don't have projectile motion in this case yet, right? It's just throwing a stone downwards. So she hears the stone splash into the water at the bottom of the well 2.3 seconds after releasing the stone. Ignore the time taken for the sound to reach the student from the bottom of the well. Calculate the depth of the well. So this is actually a very simple problem, right? Because we know that the elapsed time was 2.3 seconds, and we know our acceleration of gravity to be 9.8 meters per second. Now remember that, per second squared. Remember that you can always pause the videos and try and solve the problems yourself, and then come back to the answers. That's actually what I would advise all of you to do. Alright, so our initial velocity is also 0, right? Because it does not move in the beginning, you're just letting it go. So what's actually going to accelerate this stone, this pebble, is gravity. So that's all we have. So we have time, we have gravity, acceleration, and initial velocity. So we are looking for the depth. So we need some equation in which we have the displacement. So if you look at your notebooks or at the booklet that all of you had a copy printed that I gave personally to each one of you, you should be able to calculate the displacement as the initial velocity multiplied by the time plus half of the acceleration multiplied by the time squared. That's one of the CUVAT equations that you find, right? One of the three. Now, let's observe. So first thing, our initial velocity is 0, so this term will go away, because 0 times anything is 0. So we have our gravity and our time. Now we have to make a decision here. If we decide our frame to be positive downwards, then our acceleration will be positive and our displacement will also be positive, and we'll have to remember that we're counting distance downwards. If we decide, however, to choose our frame of reference upwards, gravity will be negative and our displacement will also be negative. And that's not what I'm going to do. I'm going to choose it downwards. So let's keep it downwards. You can choose whichever you like. Okay, this is why. So gravity will be positive 9.8 meters per second squared. I should have labeled this here, right? But, well, it's positive here nevertheless. So our displacement will also be positive. So let's see. Our displacement will be half of A is 9.8 and time is 2.3 squared. So if we do all of that, we should find this to be approximately 26 meters. This is up to 2 significant figures. So there we go. Hey, we have calculated the depth of the well. Nice. Now calculate the speed at which the stone hits the water surface. So this is A. Now for letter B, you have to remember that we have more equations, and there will be one equation which will easily give us the final speed in terms of initial speed, acceleration and time. So since we know all of those, we know that initial velocity is 0, acceleration will be our acceleration of gravity, so this is 9.8 times 2.3. That's actually very simple, isn't it? And that's what we assume. For those of you who perhaps have a keen eye, right, you can see here that, well, since my velocity is changing 9.8 meters per second squared, so that means that it's increasing by 9.8 meters per second at each second. So if 2.3 seconds have elapsed, well, I will have to take that into factor. So that's 2.3 times 9.8 meters per second faster. Well, if you cannot see it, just apply the equations and you're going to reach the results. So the velocity here, the final velocity, would be 23 meters per second downwards, right? Since I have said velocity, it's downwards. I have to say which is my direction. If I'm just saying the speed, my final speed, then that's 23 meters per second. Since the question is just asking for speed, we just need a number. If this was velocity, then you would have to state downwards. Fine. Now let us see. Explain why the time taken for the sound to reach the students can be ignored. Well, the speed of sound is very large. The speed of sound, I don't quite remember if you have this in your booklet, but you should have, I guess you should have it. Now, the speed of sound is around 300 meters per second. It's not actually that, it's around 330, 340. I used that information, for example, in my ultrasonic sensors when I do robotics. So the speed of sound is around 300 meters per second. So in 2.3 seconds, which is the time that the stone has fallen, it would take a lot of it's basically nothing if you compare the speed at which the sound travels, right, which is much faster than the speed at which the stone is falling, right? And if you compare those values, you would have about what, 4%, right? The sound, if you have the sound crossing the same distance of 26 meters, what would be the time taken? So if you want to be more exact, right, the speed is distance over time. So how much time would the sound take? So the time that the sound would take would be distance divided by speed of sound. So the distance is 26 meters. the speed of sound is around 300 meters per second. So this would be about 0.08 seconds. So it's basically negligible compared to the 2.3 seconds. It's what, around 4%, right, of the total time taken for the stone to fall. So it's negligible. You can just neglect it since it's much smaller and it shouldn't affect that much your answer. Alright, so in the last problem we only had a vertical motion. We didn't have any horizontal motion. So what would change in projectile motion? Well, hardly anything. The only difference now is that besides the up and down motion, the vertical motion will also have a horizontal motion. But the point is, the horizontal motion is always the same. Our speed will be constant throughout. So our horizontal velocity will not change. Notice that the total speed, right, the speed of our object will change. The vertical speed does change. The vertical velocity does change. However, the horizontal velocity does not. The horizontal speed does not. So it will stay the same. And well, this graph basically describes the motion of any projectile, right? And we are going to apply those equations into problems in the next slide. So let's say that we have someone in the DOV, right, shooting some arrows around, hopefully safely. So an arrow is fired horizontally from the top of a tower 35 meters above the ground. Right, so yeah, we've got a tower here, right? And then there's someone here shooting arrows, and it has been fired horizontally. So first it was horizontal, and then gravity happens and falls down, right? So this is the ground here, this is the ground, right? There you go. So 35 meters above the ground. So this distance here is 35. The initial horizontal speed, so u, is 30 meters per second. Good. So we're given the horizontal speed. What would be the initial vertical speed? Well, let's call this ux. What would be uy? That would be 0. Because, well, when the arrow is shot, it has no vertical speed at first, and then as it's moving, then gravity is happening, right? Gravity is basically, well, you have mass, so I want to push you down, I want to attract you towards me, which also have mass. So that's what the Earth does. So gravity pulls it down and it starts to accelerate down. So there's no acceleration on the horizontal movement, however there is on the vertical movement. Okay, so I've got my acceleration on y to be, let's say, if we assume that downwards is positive, my acceleration would be 9.8 meters per second squared. Alright, so first question. Calculate the time. Well, assume that air resistance is negligible. Okay, that's good. Now, the time, calculate the time for which the arrow is in the air. Well, if you notice, it will depend on the vertical motion. It will not be just about the horizontal motion. Obviously, it does have to do with the horizontal motion, but, well, no, actually, just vertical. So let's see. If we observe this vertical motion, we could use our S-UVAT equations. So S equals ut plus half at squared. I want to find the time. I know the acceleration. and I know the displacement. Well, that's fair enough. Now initial, since I'm applying this for x, for y, so displacement in y, acceleration in y. Okay, just because they will be different horizontally or vertically. So now initial velocity is 0 in y, so, and acceleration is 9.8, and this displacement is 35, so 35 equals 9.8 divided by 2 t squared. So we can find time to be 2.7 seconds. Okay, that's up to two significant figures. It would be 2.67, and then you round it to 2.7. There you go. So this has only to do with the vertical motion. Now, so that's done. Now in the second question, letter B, the distance from the foot of the tower at which the arrow strikes the ground. So it's this distance here, right? So that's our Sx. Now, since our movement, our horizontal movement, is not influenced by the acceleration, which is only downwards, we'll have a constant speed. So our displacement will basically be our speed multiplied by our time. That's as simple as that. So if we multiply those, we would have 30, which is our speed, times 2.7. And it makes sense, 30 meters per second times 2.7 seconds. So in each second, it will move 30 meters. So if I'm moving during 2.7 seconds, I'll move 30 times 2.7 seconds, meters. So that would be around 80.1, so two significant figures, 80 meters. There we go. That would be our displacement. So this is A, this is B, and now let's do C. So the velocity at which the arrow strikes the ground. So the thing about the velocity, we're asking for the vector, right? So since this is a velocity, we're looking for a vector. So we'll have a velocity forwards, which is constant, that's the same ux that we had at the beginning, and we'll have a velocity vy. Oh, well, here I can call it would be vx because it's final velocity, but since it's the same as the one in the beginning, I can just use ux. So if I add those vectors, I would have another vector pointing over there, right? That would be my final vector. I'm trying to do dashed lines here, but failing miserably. This is our final velocity. I'll just call it v, right? Okay, so what was, we first have to find our velocity downwards. Well, our velocity downwards, if we have a constant acceleration in each second, our speed is going to increase by 9.8. So this is going to be, well, our acceleration times how long? This is a bit obvious, isn't it? Should be. Now, acceleration 9.8 and time 2.3. So this should be 26.2 meters, which is 26 meters, right? If you just do two significant figures, it would be meters per second, say velocity. Meters per second. Okay, so this is the vertical component of our velocity. For us to find the final vector, now we just need what? Well, we have to just do vy squared plus ux squared and get the root of all of those. Pythagoras, right? So if we work that out, we know ux, which is 30. It's the same value that we had in the beginning, because the horizontal motion is still the same, and the vertical one, we have found a new value. So if we put those values in, we would find this to be about 39.8, which two significant figures would be 40 meters per second. Fair enough. Now, how do we find the angle? Well, if you notice here, we can calculate the angle. Well, let's say that we want to find this angle here. We can close a triangle, and this angle, SOHCAHTOA, right? So this angle regarding this side and this side, we would have that. We would have the tan of 26 over 0.2. If you don't round it, that's fine. Over 30, which is u. So we've got this over this, right? TOA, so opposite over adjacent, would be 41. So 41 degrees down the horizontal line. So another example. So an object is thrown horizontally from a ship and strikes the sea 1.6 seconds later at a distance of 37 meters from the ship. So let's write down what we know. So far we know time, 1.6 seconds, and we know a distance, some kind of displacement, 37 meters. So it's thrown horizontally and strikes the sea. So let's draw roughly a ship, right? I'm looking from ahead, from front, right? The ship's front is here. So an object is thrown sideways, so horizontally, and then it's gonna hit the ground later, and that's projectile motion. So we know that's a distance 37 meters from the ship. So this is 37, so that's Sx. And we know our acceleration, right? Let's call it positive downwards. So Ay is 9.8 meters per second squared. So calculate the initial horizontal speed of the object. So let's see. Now we're being asked the initial horizontal speed. We're given how long it has taken to fall, and we're asked, okay, what was the initial speed then? Well, it's actually too easy. It's easier than it seems. We're looking for horizontal speed. So, well, it has traveled 37 meters in 1.6 seconds. So, the speed, horizontal speed, does not change. So, position over time, displacement over time. So that's 37 over 1.6. So if it has traveled 37 meters in 1.6 seconds, how fast is it traveling? Well, around 23 meters per second. So letter B. What's the height of the object above the sea when it was fired upon? When it was fired, thrown? So what was the object's height? So what is this height? Y here, or H, I don't know, because let's call it Y, as Y, displacement Y, right? So we have to choose one of the equations that we know, and here, well, we know our CUVAT equations. So S equals UT plus AT squared over 2 CUVAT. Now initial vertical velocity is 0. This is not 0, that's acceleration of gravity, time squared, and there you go, displacement. So if we put the numbers in, it would simply be 12.5 meters. And there you go, that's the final displacement, and that's the answer.